Okay, so we're getting started with chapter 4, which focuses on mass, moles, and the empirical formula. This is really useful if you're trying to complete Lab 10, the empirical formula laboratory. And this really serves as the fundamental backbone necessary to understand solution preparation and critical aspects of formula stoichiometry that you need as you advance towards later portions of your nursing program, such as solution preparation and identifying and generating both buffer solutions and ionic solutions of defined concentration. So this is our precursor before we discuss solutions, pH, and chemical reactions. You first need to know how to calculate mass, moles, and analyze a chemical formula. Don't worry, it's simpler in practice when we go through it. So let's start off with this basic premise. So for atomic mass, all particles have a characteristic mass. So for example, if I have a penny and I put it on the scale, if I put the penny on a scale, this penny will weigh about 3.0 grams. So I can say, I know 1 penny corresponds to 3.0 grams, right? So based on the mass of a single particle, I can make a conversion factor, right? So I know I have, in every 3 grams, I have 1 penny, right? So then I can say, and I can calculate how many pennies are in 36 grams. Well, I'm trying to go from grams to pennies, okay? So then I know that if I have 36 grams, I know I have 1 penny per every 3.0 grams, and that gives me an estimate of 12 pennies, right? So in effect, we have gone from a unit of mass to a unit describing particles or the amounts of objects, right? We've gone from grams to pennies using our conversion factor. Does that make sense to everyone? This idea that particles have a characteristic mass.
Yes.
Okay. Now, it's equally important to acknowledge that the same mass does not represent necessarily the same number of particles. So if a quarter weighs 6 grams, I know I have 1 quarter for every 6 grams of quarters, right? So then, if I wanted to calculate how many quarters are in 36 grams, would someone like to take a guess if I'm trying to go from 36 grams to quarters? How many quarters are in 36 grams? Just intuitive. 6, exactly. So to show this, if we have 36 grams, if I'm going from grams to quarters, I put quarters on top. So I have 1 quarter per 6 grams, and that in turn gives us 6 quarters. Does that make sense to everyone? Does everyone see how, depending on the material that you're studying, each mass corresponds to a unique number of particles, such as pennies or quarters? Does that make sense?
Yes.
Perfect. So, what does this have to do with atoms? Well, atomic mass is strictly defined as the mass of an atom. The periodic table gives the atomic masses of the elements in atomic mass units, or AMU, per atom. This is the mass of a single atom. Atomic mass provides a means to count atoms by measuring the mass of a sample. So atomic mass has units of AMU per atom, where an AMU represents a very, very, very small number of grams. Okay, so for hydrogen, for example, the atomic mass is about 1 AMU, and this is 1 AMU per hydrogen atom, which roughly correlates to about 1.67 times 10 to the negative 24th grams per hydrogen atom. So we have, just like in our earlier examples of pennies and quarters, we have a direct relationship between the mass and the number of atoms of a given element. So for example, we're asked how many atoms of hydrogen are found in 30 AMUs of hydrogen. So setting up our solution map, we're going from AMUs to atoms. Our conversion factor in this case is going to be our atomic mass. So if we have 30.0 AMUs of hydrogen, we're going from AMUs to atoms. So as a result, we use the conversion factor of our atomic mass. So we have 1 hydrogen atom per 1 AMU of hydrogen. AMUs cancel, and we're left with 30.0 hydrogen atoms. Does this make sense to everyone? So again, we're using the same logic of unit conversions. We can take this one step further and we can calculate the mass in AMUs and convert it to grams. So in this case, we're going from 30.0 AMUs to grams. So in this case, starting off, we have 30.0 AMUs, and we know that we have 1.67 times 10 to the negative 24th grams per every 1 AMU. So punching this into our calculator, so we have 1.67 EE negative 24 times 30, and that in turn gives us a final value of 5.01 times 10 to the negative 23rd grams. Does this example make sense to everyone? So again, we're using the conversion factors of our atomic mass and the conversion factor from AMUs to grams. So to make sure everyone's comfortable with this idea, I have given you a picture of the periodic table that you'll be using momentarily. And I'd like you to calculate the mass in AMU of 16 atoms of carbon, and I'd like you to calculate the mass of 12 grams of oxygen in AMU. So let's work on this example for about 3 to 4 minutes, and then we'll discuss. And if there are any questions, don't be shy to share your questions or proposed responses in the chat or verbally. And really write out, what units are you starting from? What units are you trying to reach? This is just like our unit conversions chapter, except this time we're getting our unit conversion factors from the periodic table. So let's keep working on this example and we'll discuss in about 2 minutes. And I'd like to see some proposed responses in the chat or verbally. And I'd like to see at least 1 to 2 proposed responses before we discuss this solution. And we'll discuss in another minute. Okay, so let's talk about this example. So we're trying to go from atoms of carbon, and then we're trying to calculate the mass in AMUs of carbon. So if we look at carbon in the periodic table, we see that carbon has an atomic mass of 12.00. In other words, for carbon, we have 12.00 AMU per atom of carbon. You get the atomic mass from the periodic table. Now, with that established, we can take the atoms of carbon and calculate the AMUs. So if we have 16.0 atoms of carbon, we know that we have 12.00 AMUs per 1 atom of carbon. And that in turn gives us 192.0 AMUs. Does this first example make sense? Does this first example make sense to everyone? So to calculate mass, we take the atoms of carbon and multiply by its atomic mass in AMU. We get the atomic mass again from the periodic table, just like we did for hydrogen. Remember, each atom has a different atomic mass. Does this first example make sense to everyone?
Yes.
Perfect. So next, we're trying to calculate the mass of 12 grams of oxygen in AMU. So we're trying to go from grams to AMUs. If we have 12 grams of oxygen, we know from our conversion in 1 gram, in 1 AMU, because we're going from grams to AMUs, so AMU should be on top. in 1 AMU, we have 1.67 times 10 to the negative 24th grams. So punching this into our calculator, that in turn gives us 7.18 times 10 to the positive 24th AMU, which we round to 2 sig figs to be 7.2 times 10 to the 24th AMU. Does this example make sense?
Yes.
Perfect. So let's discuss mass to atom conversions. So using the atomic mass and AMU conversion factor, we can calculate the atoms of an element in a sample of that element. So for example, we're asked how many atoms of hydrogen are found in 3 grams of hydrogen. Keeping in mind that hydrogen has an atomic mass of about 1 AMU. So we're trying to go from grams of hydrogen to atoms of hydrogen, and our stepping stone to that is going to be AMUs, because we have a direct relationship between AMUs of hydrogen and atoms of hydrogen through our atomic mass. So if we have 3.0 grams of hydrogen, we know that we have in 1 AMU, we have 1.67 times 10 to the negative 24th grams. AMUs are on top because we're converting to AMUs. Next, if we're going from AMUs to atoms, in 1 atom of hydrogen, we have 1.00 AMUs. AMUs cancel, grams cancel. We're left with atoms of hydrogen. And if we punch this into our calculator, we have 3.0 over 1.67, and that gives us 1.796 times 10 to the 24th hydrogen atoms, which we round to 2 sig figs as 1.8 times 10 to the 24th hydrogen atoms. Does this make sense to everyone?
Yes.
Perfect. So what I want us to look at next is, let's look at another conversion where we're asked to calculate the mass in grams of 6.02 times 10 to the 23rd atoms of hydrogen. So in this case, we're going from atoms of hydrogen to grams of hydrogen, and we're going to go through AMUs for now. If you are reading ahead in your book and looking over this chapter ahead of time, this number may look familiar to you. So starting off, we have 6.02 times 10 to the 23rd atoms of hydrogen. We know for hydrogen, we have 1.00 AMU per hydrogen atom. And we know in 1 AMU, we have 1.67 times 10 to the negative 24th grams in 1 AMU. And punching this into our calculator, we get 1.00 grams of hydrogen. Does this make sense?
Yes.
Perfect. So to check that everyone's comfortable with these topics, I've provided you a periodic table, and now I'd like you to solve the following problem, and I'd like you to tell me how many atoms of nitrogen are in 140 grams of nitrogen. And remember, you need to use your periodic table to find your atomic masses. So let's work on this problem for about 3 to 4 minutes, and then we'll discuss. And we'll discuss this example in about another 2 to 3 minutes. Sure, I can pan up to the previous problem. And let's try to get a few more responses in the chat before we discuss in about 1.5 to 2 minutes. These are the kind of bread and butter calculations you'd likely have to do as part of solution prep and other aspects of calculations, for example, in buffer prep. You need to calculate atoms and eventually calculate moles, and these calculations are building towards that. And let's try to get a few more proposed responses in the chat before we discuss in about another minute. And let's try to get a few questions and proposed responses in the chat before we discuss. Proposing your solution is invaluable before we go over these problems because it allows you to look at different aspects of how you went about solving a problem and correct and modify your logic and problem solving process. Does anyone have a proposed solution for this problem? Okay, we're starting to see a few in the chat. So let's discuss just to give everyone a little bit of guidance here. So setting up our solution map, we're trying to go from grams of nitrogen to atoms of nitrogen. And to calculate atoms of nitrogen, we're going to need to figure out the AMUs of nitrogen. Okay, so looking at the periodic table, if we go and find nitrogen in the periodic table, it has an atomic mass of 14. So we have 14.00 AMU per atom of nitrogen. Okay, perfect. So then if we have 140 grams of nitrogen, we're going from grams to AMU. We know that in 1 AMU of nitrogen, we have 1.67 times 10 to the negative 24th grams. We also know to go from AMUs to atoms that in 1 atom of nitrogen, we have 14.00 grams. Oh, sorry, 1 atom of nitrogen, we have 14.00 AMUs. I'm getting a little bit ahead of myself here. You'll see why in a moment, but there's a faster way to get through this problem that goes through moles rather than AMUs. Okay, so just to summarize, we went from grams of nitrogen to AMUs using our conversion factor, and then we can go from AMUs of nitrogen to atoms of nitrogen using our atomic mass. So punching this into our calculator, we have 140 over 1.67 over 14, and that gives us 5.988 times 10 to the 24th atoms of nitrogen that we round to 6.0 times 10 to the 24th atoms of nitrogen. Does this example make sense?
Professor, how do you get the 5.988 again?
Oh, so punching this in, I take 140 divided by 1.67 divided by 14.
Okay, got it.
Are you getting the same result from your calculator?
I haven't calculated yet, but I can right
Okay.
Professor, I have a quick question. So
Yeah.
what 1.67 times 10 to the negative 24th, how did we get 24? We just
This is our known conversion factor where 1 AMU corresponds to 1.67 times 10 to the negative 24th grams.
Oh, okay. So then when we put it in, it would be a positive 24 instead of a negative 24.
Exactly.
Okay.
Because when you divide by a negative power of 10, you end up with a very large number as
Okay.
your output.
Gotcha.
Does that make sense?
Yes, thank you.
Perfect. Okay. So let's keep going now, and let's work on the next 2 examples. We're asked to calculate the mass in AMUs of 2.33 times 10 to the 16th atoms of sulfur. You're going to need to find sulfur in the periodic table. And then I'd like you to calculate the mass in grams of 3.4 times 10 to the 12th atoms of bromine. And again, you're going to need to find bromine in the periodic table. Let's work on these examples for about 4 to 5 minutes. Don't be shy to share your proposed solutions in the chat, and then we'll discuss these examples in about 4 to 5 minutes. And again, I encourage you to share your responses so that way when we go over the solution together as a class, you can revise your proposals and in turn hone your logic that you're using to solve these problems. And if there are any questions at all during these problem solving sessions, don't be shy to ask them in the chat or verbally, and I'd be happy to address your questions. And we're starting to see some proposed responses in the chat. Let's keep working through these problems. And we'll discuss in about another 4 minutes. And if there are any questions I can address, again, don't be shy to ask them verbally or in the chat. I'd like to see a pool of responses for each of these 2 questions, and then we'll discuss in about another 3 to 4 minutes. And let's try to have some contributions from a range of different students, and we'll discuss in about another 1.5 to 2 minutes. And if you have a question, if there's any part that you're unsure about, don't be shy to ask. The best way to often get used to these kinds of conversion problems is to attempt them, propose a solution, and then revise your solution if needed in response to feedback. Okay, so let's take a look at this example. So we're asked to calculate the mass in AMUs of 2.33 times 10 to the 16th atoms of sulfur. So we're trying to go from atoms of sulfur to grams of sulfur, and our stepping stone is going to be AMUs of sulfur. So if we look up sulfur in the periodic table, what is the atomic mass of sulfur? What is the atomic mass of sulfur?
32.05.
Yep. So we have 32.05 AMUs per atom of sulfur. Okay, perfect. So then to go from atoms of sulfur to AMU, we're going to take our initial mass, or our initial number of atoms. And since we're going from atoms to AMU goes on top. So we have 32.05 AMU per 1 atom of sulfur. Atoms cancel. And then to go from AMUs to grams, we know we have 1.67 times 10 to the negative 24th grams per 1 AMU. And now punching this into our calculator, 2.33 times 32 times 1.67, that gives us 124.5 times 10 to the negative 8 grams that we simplify to 1.24, sorry, not 1.24, 1.25 times 10 to the negative 6th grams. Does this example make sense?
Why this time mass is in AMU, not in G, in gram?
Ah, yes. Let me show the mass in AMUs. Let me show the mass in AMUs just to start off. If we wanted to calculate just the mass in AMUs, then we'd stop after the first step.
But your question is asked what's the mass in AMU, not in gram.
Yep. I'm just showing how to calculate the mass in grams because it's an extension of the calculation from AMUs. If we stop just at the mass in AMUs, we'd just perform the first step of this calculation, and that would give us 7.47 times 10 to the 17th AMU.
Okay, gotcha.
Yeah. So I'm showing how, depending on how far you take the calculation, you can either get the mass in AMUs or the mass in grams.
But for this problem, the answer would be the 7.47 times 10.
Yep, you just stop at the mass in AMUs because that's what the problem is asking. In the next case, we're asked to calculate the mass in grams of 3.4 times 10 to the 12th atoms of bromine. So we're trying to go from atoms of bromine to grams. And again, we're going to go through AMU. If we look up bromine in the periodic table, what is the atomic mass of bromine? What is the atomic mass of?
79.904.
Yep. So 79.90 AMU per atom of bromine. Okay. So we're going to start off with our atoms of bromine. And then to go from atoms of bromine to AMU, we multiply by our atomic mass. And then to go from AMU to gram, we use our conversion factor of the form gram per AMU. So punching this into our calculator, we get as our total for our final mass 4.5 times 10 to the negative 10th grams of bromine. Does this example make sense to everyone? Does this example make sense?
Yes.
Any questions on these examples? So let's keep going now, and let's look at another guided example where this time we're directly calculating the atomic mass. So in this question, an element is discovered that has a mass of 3.2 times 10 to the second AMU for 15 atoms. So we're asked, what is the atomic mass? So atomic mass is the mass in AMU per atom. So to calculate our atomic mass for this new element, we're going to take the mass in AMU and divide it by the number of atoms. So punching this into our calculator, we have 320 over 15, and that gives us a mass of 21 AMU per atom. And what element has a mass of 21 AMU per atom? What element has an atomic mass of about 21?
Neon.
Yep, so this likely would be either, so we can say that it's pretty close to that of neon. It's not exact, but neon would be a reasonable assignment.
Can I also say sodium? Because
Yep.
sodium.
Yep. Yep. We don't have enough precision to tell right now. And that's partially because we haven't measured the mass to a really exact number of significant figures. We only have 2 sig figs in this measurement. The more precision we have, the more accurate the more precision we have, the more likely we are to get an accurate match for our atomic mass.
So that the 3.2 times 10 to the 2 U means stands for AMU.
Yep, exactly. U is just another way of writing out AMU.
Okay.
Perfect. So now that we've seen an example of calculating atomic mass, I'd like you to take a look at the following problem. We know that 1.5 times 10 to the 25th atoms has a total mass of 398.7 grams. I'd like you to calculate the atomic mass in AMU per atom, and I'd like you to tell me what element this sample is. What element is this sample? So let's take about 3 to 4 minutes to work through this example, and then we'll discuss momentarily. And if you have any questions, don't be shy to ask in the chat or verbally, and don't be shy to write your proposed responses in the chat. Just as a reminder, this is the conversion factor that relates AMUs and grams, which you'll likely need to solve this problem. And we'll discuss this example in about another 2 minutes. I'd like to see a few more student responses before we discuss, just so that way we can have a pool of proposed responses and element assignments. And it's great to see that the students in the class are participating and sharing their reasoning and logic when solving these problems. And we'll discuss in another minute. Okay, so let's discuss. So first thing we need to do, if we want to calculate the atomic mass in the form AMU per atom, we first need to convert our mass in grams to AMU. So we have 398.7 grams, and we know that in 1 AMU, there are 1.67 times 10 to the negative 24th grams. So punching this into our calculator, we get in turn 2.387 times 10 to the 26th AMU. Now to calculate our atomic mass, we need the mass in AMU per atom. So we take our mass in AMU and we divide it by the number of atoms. So punching this into our calculator, that in turn gives us 15.9 AMU per atom, which is pretty close to the atomic mass of oxygen. So we tentatively assign this sample as a sample of oxygen. Does that make sense to everyone? Any questions so far? Okay, so let's keep going now and let's talk about molecular weight or molar mass. So molecules are composed of 2 or more atoms. Compounds are composed of 2 or more different elements. The mass of a molecule, or the molecular weight, is a sum of the atomic masses of all atoms in that molecule. Molecular weight can also be written as molar mass or molecular mass. So the number of each atom of each element in a given molecule is given by the molecular formula subscripts. So for example, we can calculate the molecular weight of molecules by adding up the mass of each of our individual atoms. So for example, for chlorine, which is Cl2, I know my atomic mass is 35.45 AMU per chlorine atom, and I multiply it by 2 because I have 2 chlorine atoms. That gives me an atomic mass, this gives me a molecular mass or molecular weight of 70 0.90 AMU per chlorine molecule. We can do the same thing for more complicated polyatomic species. So we know for sodium, I have a mass of about 22.98 AMU per sodium atom, and I have 2 sodium atoms. For sulfur, I have a mass of 32.00 AMU per sulfur atom, and I have 1 sulfur atom. And for oxygen, I have 16.00 AMU per oxygen atom, and I have 4 oxygen atoms. So punching this into my calculator, 22.98 times 2 plus 32 plus 16 times 4, that gives me a molecular weight or molar mass of 141.96 AMU per molecule of sodium sulfate. Does this idea make sense to everyone? Does this idea of calculating molar mass make sense?
Yes.
Now, this can even be applied to isotopic species. In this case, H2O18. So we know we have 18.00 AMU per O18 atom. Remember, this 18 is telling us our mass number, which is pretty close to the atomic mass for that isotope. We have 1 O18 atom. And for hydrogen, we have 1.00 AMU per hydrogen atom. And of course, we have 2 hydrogen atoms. So this would give us a preliminary molar mass of 20.00 AMU per H2O18 molecule. So we can either get the atomic mass on average from the periodic table or for a specific isotope using the mass number. Does this make sense to everyone?
So the 18 goes in front of the oxygen?
Yes, and that's denoting that we're dealing with the O18 isotope.
Okay.
Does that make sense?
Yes.
Perfect. Okay, so let's try to apply what we've learned, and this will be the last example set for today. And I'd like you to calculate the molecular weight of the following 3 molecules. So let's spend about 4 minutes on this example, and I'd like to see molar mass calculations for each of these molecules, and then we'll discuss momentarily. And if you have any questions on these problems, don't be shy to ask them in the chat or verbally. And we'll discuss in about another 2 to 3 minutes. And don't be shy to share your proposed molar mass calculations, and we'll discuss momentarily. And we'll discuss this example in another minute. Okay, so let's discuss this example. So in ozone O3, oxygen has a mass of 16 AMU, and we have 3 oxygen atoms. That gives us a mass of 48 AMU. In barium phosphate, we have 3 barium atoms, 2 phosphorus atoms, and 8 oxygen atoms. You're going to need to be really comfortable with identifying the atoms in a formula to accurately calculate the atomic mass. So barium has an atomic mass of 137.3 AMU per barium atom. We have 3 barium atoms. For phosphorus, it has a mass of 31.0 AMU per phosphorus atom, and we have 2 phosphorus atoms. And then oxygen has a mass of 16.00 AMUs, and we have 8 oxygen atoms. Punching this in, we have 137.3 times 3 plus 31 times 2 plus 16 times 8, and that gives us a mass of 601.9 AMU per molecule of barium phosphate. Does this make sense? Does this make sense to everyone so far? Notice how we're applying the skill that we learned last class session. Finally, for ammonium carbonate, we have 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. So we know nitrogen has a mass of 14 AMU per nitrogen atom, and we have 2 nitrogen atoms. Hydrogen, we have 1.00 AMU per hydrogen atom, and we have 8 hydrogen atoms. Oh, one moment, sorry about that. OneNote had a small crash. Let me share my screen once again. And let's continue on right where we left off. So for hydrogen, we have 1.00 AMU per hydrogen atom, and we have 8 hydrogen atoms. For carbon, we have 12.00 AMU per carbon atom, and we have 1 carbon atom. And then for oxygen, we have 16 AMU per oxygen atom, and we have 3 oxygen atoms. So punching this into our calculator, we have 14 times 2 plus 8 plus 12 plus 16 times 3, and that gives us a molar mass of 96.00 AMU per molecule of ammonium carbonate. Do these examples make sense to everyone? Do these examples make sense?
Yes.
So that's all I have for today's scheduled class session.